There are going to be a couple of key equations of straight lines. When we get to talking about linear functions, it's going to be the slope-intercept form, y equals mx plus b. I know you've seen this before. But there'll also be some important applications where the standard form of the equation of a straight line comes into play. Standard form, right there, ax plus by equals c. When we put the c on the left-hand side, it's real similar to this. We call it general form. Basically, this standard form or general form, which is similar, is what to use if you're looking at an equation with x's and y's in it, and you're asking yourself the question, is it linear or not? Is the graph going to be a straight line or not? You see an equation, there are x's and y's. What's the graph going to look like? Maybe it's a straight line. If it is a straight line, you'd like to be able to recognize that before you go plotting points, because if you can nail it down and say guaranteed to be a straight line, all you need are 2 points, and you can graph the line. So if the equation we're dealing with has nothing other than x terms, y terms, and constant terms, no x squared, no y squared, x cubed, y cubed, no square roots of variables, no variables multiplied together, no variables in the denominators, x terms, y terms, and constant terms, nothing but that, it's guaranteed to be a straight line. So standard form of a linear equation, and then from that we can take that, solve it for y if it has a slope. If it has a slope, we can put it in slope-intercept form. Now we do want to look at key characteristics of straight lines. The points where the straight lines intersect the x-axis and where they intersect the y-axis are going to be important. Also the steepness of the line. When we talk about functions, whether they're linear or nonlinear, we're going to be concerned with the rate at which the function value is changing. If it's changing really rapidly or not so fast, or if it's going maybe in a negative direction, we want to be able to quantify that. So the slope of the line becomes very important. Slope is basically a number, a real number that we can assign to a line as an indication of how steep the line is. So if we've got say a couple of lines that are both rising as we go from left to right, say that one and maybe this one right here, what we want to compare is the ratio of the vertical change, I guess I should write it in that direction, to the horizontal change that takes place when you move from one point, x sub 1, y sub 1, to another point, x sub 2, y sub 2 on the line. Similar sort of thing here. If you move from the point x sub 1, y sub 1 to the point x sub 2, y sub 2 on that straight line, we want to compare the vertical change, it's almost vertical, to the horizontal change that takes place. If when you compare, the vertical change is not nearly as much as the horizontal change, basically the ratio, you divide the vertical change by the horizontal change. If the vertical change, the size of it doesn't compare favorably with the horizontal change, the slope is smaller. Okay, it's a lower value for the slope. On the other hand, if there's quite a bit more vertical change than there is horizontal change when you move from one point to another point on the line, the slope's going to be greater. So the value of the slope is going to be greater. So the slope, just in general, is a number that we assign to the line as an indication of the steepness of the line. Now what we'll see is when the slope is negative, what's happening? Yeah, it's going down, decreasing as we move from right to left, and depending on the value, if it's cost to your company that's going down, like, okay, that's great, it costs less to do business. But if it's profit that's going that direction, that maybe is not so good. So we consider the slope here. The slope formula, m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. As we move from point to point on the line, we'll use that to calculate the slope when there is a slope. 4 basic cases here If the line is rising as we move from left to right, the slope will be positive. For really steep lines, really large positive slopes, close to horizontal, but still increasing, really small positive slopes close to zero. If the line slants downward to the right, as we indicated, the slope is negative. Basically, moving downward is negative vertical change when moving to the right. So a negative vertical change divided by a positive horizontal change is going to be a negative number. If it's not too steep, it's just a small negative number, but if it's really steep, it can be a great big negative slope, and depending on the situation, that might not be so good. If the line goes straight across, horizontal lines have a slope. Doesn't look all that steep, but there is a number that we can assign to a horizontal line that functions as its slope, and that's 0. Okay. If you say, okay, we're going to go, how far up do we go when we go 100 units to the right? Well, 0. There's actually an answer to that question. So there's a slope of 0 for that line. It has a slope, and the slope is 0. The one that's troublesome sometimes are the vertical lines. Vertical lines, if you ask the question, if we go 1 unit to the right, how far up do we go? There's no answer to that question because we can't go 1 unit to the right if we're on a vertical line. So attempting to find the slope of a vertical line is an exercise in futility because you can't divide by the change in x because the change in x is 0. So the slope of a vertical line is undefined. Basically, it doesn't have one. If you are familiar with the expression no slope when considering the slope of a line, it's okay to use that in conjunction with a vertical line because a vertical line does not have a slope. I would emphasize that you probably should say something like no slope at all if you're going to use the expression no slope, because a horizontal line has a slope. It happens to be 0, but it has a slope. So when using the expression no slope, reserve that for vertical lines. Let me paste the other one in here as well for horizontal lines. I'll say this. It has a slope. The slope is 0. There we go. So, vertical lines versus horizontal lines. Examples, make some examples here. Here we go. Example 1, given a couple points, they determine a unique straight line. If it has a slope, we want to be able to find the slope of that straight line. No picture is required for this. That won't usually keep me from drawing one in the course of doing an example, because we're going to calculate a number, and it's good to know what would the line look like that would have a slope that's that particular number. So first the picture, we've got the point 2, -1. Let's say 1, 2, and then -1, and then the point 1, 2, 3, 4. 1, 2, 3. So the point 4, 3. So 4, 3 right there. 2, -1 right there. Connect the dots. Is this line going to have positive slope, negative slope, 0 slope, or no slope at all? Positive slope. Positive slope, and pretty good size slope, I would guess. M equals 3 minus -1. That tells us how far up we go, moving from point to point, over 4 minus 2. That tells us how far to the right we go. So the rise looks like 4, and the run looks like 2. So 4 divided by 2 equals 2. So positive slope, the slope is 2. B part, I'll get to use the point 2, -1 again. 1, 2, -1. 2, 3, 4, 5. The 2 points have the same x coordinate. When the 2 points have the same x coordinate, technically, we're not supposed to even use the slope formula. It's really not even defined if the 2 points have the same x coordinate. I'm going to throw caution to the wind and attempt to use it nonetheless. M equals 5 minus negative 1. That's how far up we go for moving from point to point. But 2 minus 2. We do not go to the right or left at all. And this is undefined. Undefined. It's not enough. It's not good enough to leave your final answer 6 over 0. I really can't promise you much, if any, partial credit at all for writing it 6 over 0. You need to tell me what that means. Yes?
So we have to work it out even though we know it's undefined?
Actually, no. It is really not necessary to show your work. Just kind of a casual glance will show you. Just noticing that the x coordinates are the same. That's enough. And just say undefined, and I can't see, if you say undefined slope or no slope at all, I can't see taking off any points at all, because I think you've looked at it and kind of figured it out. Not a whole lot of work is necessary, and you can do that without really writing anything down. The last one, what if you look at this and notice the y coordinates are the same? What can you conclude from that? It's a horizontal line. And what do we say about the slope of the horizontal line?
0.
It is 0. It has 1, and the slope is 0. I'll go ahead and use the slope formula, though. Negative 1 minus negative 1 over 4 minus 2. That's 0 over 2. Probably give you a little partial credit if you leave it 0 over 2. Maybe half credit if you leave it 0 over 2. But you have to understand, not everybody in Okaloosa, Walton, Santa Rosa counties knows that 0 divided by 2 is 0. And you want to convince me that you're one of those particular few who does know that 0 divided by 2 equals 0. So go ahead and say equals 0 there for full credit there. That's what you want. All right. We mentioned slope-intercept form, y equals mx plus b. By inspection, when an equation is in that form, the slope is the coefficient of the x on the right-hand side is the m, and the y-intercept is b. And it makes it relatively easy to sketch a quick graph of a function, of an equation that's in slope-intercept form, because we can use the y-intercept to plot an initial point, and we can use the slope to find an additional point. Example 2. The first two look like they're in slope-intercept form. We might have to do just a little bit to the other one to get it into slope-intercept form. Y equals 2x plus 3. By inspection, we tell that the slope is what? 2/3. We notice it's in slope-intercept form because we have one y on the left, no y's at all on the right, just an mx plus b. The slope is 2/3. The y-intercept, I really should start saying the intercept on the y-axis, because I like to think of it as a point rather than just a number, is 0, 1. There it is. So if we begin with the point 0, 1 and the 2 over 3, we use that. And let's see, since 2 is the vertical change, positive 2 would indicate we could move from that point and go 2 up. Since 3 is the horizontal change, that should mean we could start at our point and go 3 to the right. That's one way to do it. 2 up and 3 to the right. We should be able to find as many additional points as we need. So from there, we can go 2 up and 3 to the right. If we need the specific coordinate, certainly we can add 3 to the x coordinate and get 3, and add 2 to the y coordinate and get 3. And if we've got a good straight edge, we should be able to connect those dots. But if you want another one, 2 more up, 3 more to the right, add 3 more to the x coordinate, add 2 more to the y coordinate. If we were up against it in the upper right-hand corner of our graph, and we needed some points down and to the left, we could find those as well, right? We could take 2 over 3, and actually negative 2 over negative 3 would also equal 2/3. So we could go 2 units down and 3 units to the left and find some additional points that way. So negative 3, negative 1. So connect the dots with the straight line. And there we go. Beginning with the y-intercept, using the notion of slope, rise over run, vertical change over horizontal change, we can find additional points on the line. Quickly, the b part, y equals 3x minus 1. The intercept on the y-axis is 0, negative 1. The slope is 3. I'm going to write it 3 over 1. It's kind of lame. I should have given an example of one with a negative slope, but maybe the next one will have a negative slope, but that's fine. 3 up, 1 to the right. So how about 3 up and 1 to the right, taking us to the point 1, 2. Add 1 to the x-coordinate, add 3 to the y-coordinate, and connect the dots. I don't think we need to spend any more time on that one. Good graph of y equals 3x minus 1. The c part is not in slope-intercept form. We need y all by itself on the left, and that's not what we have. How do we get there from here?
Subtract x.
Subtract x from both sides. So minus x, and we'll have 2y equals negative x plus 3. Divide both sides by 2. So 2y divided by 2 equals negative x plus 3 divided by 2. Y equals negative x over 2 plus 3 over 2. So y equals 1/2. Sorry, negative 1/2 x plus 3/2. Okay. Now we could begin at the y-intercept if you like. The intercept on the y-axis, 0, 3/2. But I think if we go 1 down and 2 to the right, 1 down and 2 to the right, from there, all the points we plot, at least the y-coordinates, would be fractions. Can we stare this thing down, use the stare at it and hope a solution jumps out at you method, and find an ordered pair, both of whose coordinates are whole numbers, that satisfies this? 3, 0. If x equals 3, y equals 0, that makes this true. So instead of starting at 0, 3/2, where we could, but I'm just not crazy about that, start at 3, 0. And from there, if we're using our slope, you can think of it negative 1 over 2, negative 1 indicating go 1 unit downward, and then 2 to the right. So 1 down and 2 to the right, 1 more down and 2 to the right. Additional points, 5, negative 1, 7, negative 2 it looks like. And if we wanted to, we could go, what, 1 up, 2 to the left, 1, 1 also is a solution to this. So we connect the dots and we have the graph, and there's that y-intercept, 0, 3/2. And these are sorts of things. Probably the A part, the B part, you punch them into your calculator, the right-hand side just as they are, because they're already solved explicitly for y. The C part, you do need to put that in slope-intercept form before punching the right-hand side into the calculator, but the calculator should give you a pretty good sketch of each of these graphs pretty quickly and easily. If we have some information about a line, some of the applications in the next section, we'll have some data points that are given, and we'll need to be able to construct a linear function that kind of matches that particular set of conditions. If we know, for example, a point on the line, and either someone tells us or we can figure it out on our own, the slope of the line, we'd like to be able to write an equation of that line. Now, the Alex way of going about this, I don't particularly care for. and it actually grieves me deeply to work the problem like this, but I should probably go ahead and do it anyway. The Alex way of doing things goes like this. We know y equals mx plus b is the equation of a straight line if it has a slope. This tells us the slope, -4. It also tells us a point on the line, 2, -3. So that's 3 out of 4 of the letters of the alphabet that we find in this equation. If we'll substitute 3 out of 4 of those letters of the alphabet, the only one that's missing, B. We can solve that for B, and it will be the B that goes in our equation. So here we go. -3 equals -4 times 2 plus B. Am I even doing this right? This hurts so deeply. Does this look okay? All right. -3 equals -8 plus B. Add 8 to both sides. Plus 8 plus 8. 5 equals B. So the slope was given to be -4. The y-intercept we just found is 5. So our equation, y equals -4x plus 5. I guess what's going on here, if we know the slope is -4, the line looks something like that. A lot of different lines that have a slope of -4, but there's only one that goes through the point 2, -3. So we just take that and slide it up, slide it down until it passes through the point 2, -3. And when it passes through the point 2, -3, we look and say, what's the y-intercept? Oh, 5. And then we've got it, and we write down the final answer. That's kind of what's happening here, as far as I can tell. I don't like this particular method of finding the equation of a straight line, in case you haven't picked up on that one. Much prefer point-slope form. Much prefer the point-slope form. So let me paste this in here and redo the example. I don't know if everybody else is going to prefer the point-slope form, but I like it a lot better. Let's try the same one using the point-slope form of the equation of a straight line. I like this because to find an equation of a line, what we're having to do is substitute, not solve. Okay. Once we write the equation, we actually will have to solve for y to put it into slope-intercept form, but we have the equation before we solve anything. We're not solving something to get the equation. That's the advantage I see in this. And they're also, I'm asking for a quick show of hands. Who's got calculus on your list of things to do? Yes. All right. Yeah. When you want to write an equation of the tangent line to a point, and you take the derivative and you find the slope of the tangent line, you don't want to have to stop and solve for b every time you do that. You like to write that in terms of the slope and the point slope form just works nicely into that process, and it's a better way to go. So here it goes. The point that we have, our x sub 1 and our y sub 1 is 2, -3. So this is going to be y minus -3 equals -4 times x minus 2. Substitution. You're not solving anything, just substituting the coordinates of the point for the x sub 1 and y sub 1. Substitute the -4 for the m. This is an equation of the line that goes to the point 2, -3 and has a slope of -4. And we've done nothing other than just substitute. Now, final answer needs to be in slope-intercept form. So let's go ahead and say y plus 3 equals -4x plus 8. And then one more step, subtract 3, subtract 3. Y equals -4x plus 5. That felt so much better. Yes. I don't know how you felt about it, but that was way better for me. All right. So using the point slope form of the equations of the line, we substitute the coordinates x sub 1 and y sub 1, substitute the given value for m, solve for y. That puts the equation into slope-intercept form, and then you've got it there. This does not work for vertical lines. If you want to find the equation of a vertical line, point slope form will not get that to you because vertical lines do not have a slope. But it's pretty easy to find the equation of a vertical line another way. I guess I just did that, didn't I? All right, example 5. Find the equation of each line. I don't know if we even need to do the A part. We've kind of been there and done that. How about the B part? 2 points are given. Whoa, one way down there in the third quadrant. So 6, -1 is about right there. And -10, -9 down there somewhere. Looking like, whoa, missed both of them. Try that again. Okay, a little wavy there, but that's roughly the line that we're talking about. -10, -9. Is that the only straight line that goes through both of those points? Yeah, that's it. Any other straight line that goes through both those points is going to lie right on top of that straight line. So that's the only one. It's unique. To find an equation of that line, we need a point and a slope. And we have a couple of points, but we don't yet know the slope. So what do? We're going to use, very good, we're going to use the point slope form. But first,
find the slope of the line.
Find the slope of the line, using the slope formula. Slope formula, yes. So, -9 minus -1 over -10 minus 6. So from a y coordinate of -9 to a y coordinate of -1, looks like we're going, uh-oh. So the way I've done this, it's okay, but this evidently is my x sub 1, y sub 1, and this is my x sub 2, y sub 2. So down 8 units, so -8 right there, down 8 units from the point 6, -1, and then to the left. How far to the left are we going? 16 units to the left? That's what?
It would just be 1 half.
Yes. Reduce to lowest terms. Definitely. That's way better. So that's equal to 1/2. Okay. So now we have actually more information than we need. We needed both points to find the slope, but once we find the slope, we just need one of those. So we get to pick which point you like better: 6, -1, or -10, -9. 6, -1 is more positive than the other one, it would seem. So let's go with that. Y minus -1 equals 1/2 times x minus 6. That's an equation of this line. We just need to put it in slope-intercept form. So y plus 1 equals 1/2 x minus 3. Subtract 1 from both sides. Y equals 1/2 x minus 4. All right. How do we feel about this equation? Does it look okay? If you're working through this, I mean, one way to check your answer is to click next, and Alex will let you know how well it went. Another way to check your answer, let's say it's on a test and you don't have a next button, you could just make sure that both these points satisfy this equation. Straight line, if both these points make this equation true, then you should feel really good about it. So 1/2 of -10, put that x in for x, 1/2 of -10 is -5. -5 minus 4 gives us -9 for the y coordinate. So certainly -10, -9 works. I'm feeling pretty good about 6, -1 at this point. 1/2 of 6 is 3, and 3 minus 4 does give us a y coordinate of -1. So take the points, plug them back in for x and y, make sure they both make it a true statement, and then you sleep extra well the night after working that problem, I guess. All right. Oh, special cases. Got to do the special cases here. I don't know if there was a C part. If there was, I'll just leave it skipped. Probably wasn't important. Vertical line. We want to write an equation for the vertical line that passes through the point -2, -7. It's not possible to use either slope-intercept form or the point-slope form of the equation of the line to find this, because it doesn't have a slope. Got to have a slope to have a point-slope form or a slope-intercept form. Let's see what it does have. So -2, 1, 2, 3, 4, 5, 6, 7. We know where this line is. It goes to the point -2, -7, and it's vertical. So it also goes through the point -2, 0. That one right there. Let's see, what other points are on this line? Maybe -2, -2 is on there. How about -2, -8? That's on there. What else? Where's that point right there? -2, -4. That's definitely on there.
-2, -100.
Yes. Yes, not in my viewing window here, but that's on there. So we ask ourselves, what do all these points have in common? The x-coordinate's -2. So how about, here's my proposed equation. X equals -2. Basically what we have is the set of points in the plane whose x-coordinate is equal to -2. And if your x-coordinate is equal to -2, you're on this line. If you're on this line, your x-coordinate is equal to -2. So it's as complete a description of the set of points on this line as we need. Now we said the standard form of the equation of a straight line. Where was that standard form? Where was it? Ax plus by. Was it way up there? Yeah, there it is. Ax plus by equals c gives us the equation of a straight line. Now, the qualification there is a and b can't both be 0. That kills both the x and y variables, and you've just got 0 equals c, and that doesn't give you any points. But it could be that one or the other, a or b, could be 0. In the case of a vertical line, b does equal 0 there, and you don't have a y term. So in the case of a vertical line, it's just x equals a constant. In the case of a horizontal line, what's going to happen? There's the point. We know it's a horizontal line because it's given. So it looks like this, and definitely includes the point 0. Whoops. Yes, that's right. 5. 0, 5 is what I want. We could actually use either the slope-intercept form or the point-slope form for this if we wanted to. Do we want to? No. No. Just a few more, because it has a slope, right? It has a slope. The slope is 0, but we don't have to use that if we don't want to. Negative 4, 5. Negative 1, 5. 2, 5. 6, 5. What would be a good equation for this line? Y equals 5. There we go. So in the equation of a horizontal line, y equals a constant. There is no x variable in the equation of a horizontal line. Because the impact of x wouldn't really change anything. You can let x be whatever it is. Y is going to be 5. That's really all that matters if you're on a horizontal line. So y equals a constant. Was there a C part? Nope. I must have deleted that. All right. If we sketch the graph of a straight line, would that, I'd ask this, could that determine a function? And would that always determine a function? Graph of a straight line. Is it a function if it has positive slope? Taking vertical line test here. That passes the vertical line test nicely. Is it a function if it has negative slope? Yes, passes the vertical line test. Is it a function if it has zero slope? Close to horizontal, slightly negative maybe. Yes, this too passes the vertical line test. Is it a function if it has no slope at all? No. Fails the vertical line test miserably, right? If it's a vertical line. So, this is a yes, this is a yes, this is a yes, and this is a no. Okay, so as long as it's not a vertical line, it will determine a function. So we can write it in the form y equals mx plus b, so long as it has a slope. And if once we establish that it's a function, because it's one of these lines that pass the vertical line test, give it a name suitable for a function like f. That'd be a good name for it. Pick up the y, replace it with f of x, and we've got ourselves a linear function. The graph of f of x equals mx plus b is exactly the same picture as the graph of y equals mx plus b. It's just given a different name. We acknowledge that it's a function, we call it f, and so we've got ourselves a linear function. So in this next example, if we want to write a linear function that has these two function values, we first need to realize the information that's being given to us. When we know two function values and the x coordinates that go with them, or the domain elements that go with them, it's actually telling us 2 points on the graph. So rephrase this: find an equation of the straight line that passes through the points -8, 7 and 10, -2. Just a fancy function notation way of asking exactly that same question we did a few minutes ago. So we find the slope using the slope formula, find an equation using the point slope form. Please use the point slope form. Find an equation that way. And then third, put it in slope intercept form. Fourth, pick up the y, replace it with f of x. So we can do this. Step 1, m equals -2 minus 7 over 10 minus -8. Looks like -9 over 18, or -1/2. -1/2 for the slope. Step 2, point slope form. I'm going to write down the point slope form and then I'll substitute. We're going to be using y minus y sub 1 equals m times x minus x sub 1. Excuse me. Either point will work. Anyone really strongly prefer the 10, negative 2, or would it be okay to use the negative 8, 7 since it's already conveniently labeled x sub 1, y sub 1? That'd be good. Y minus 7 equals negative 1/2 times the quantity x minus negative 8. Simplify the minus and negative inside the parentheses first. Negative 1/2 times x plus 8. That might be a good reason for not using a negative x coordinate if you can avoid it, because there's that extra step. If it's minus and negative, it's just better to call that plus a positive before moving on. Distribute the negative 1/2 across the parentheses. Negative 1/2 of 8 is going to be negative 4. And then add 7 to both sides. Negative 1/2 x plus 3. So that's basically step 2 and step 3 in one. The writing down point slope form and then solving for y, it just kind of blends naturally together there. Step 4, pick up the y, replace it with f of x. Maybe. Yeah. And then step 5, want to check it? Check. Step 5. You don't have to check. It's not like the radical equations where you do everything right and still get the wrong answer. It's not like that. And we have not made a mistake. We have the right linear function, but let's check it anyway. Check. What is f of negative 8 here? Negative 1/2 times negative 8 plus 3. That's 4 plus 3, which is 7. So f of negative 8 does in fact equal 7. And what about f of 10? Negative 1/2 times 10 plus 3 is negative 5 plus 3, which is negative 2. This linear function does exactly what we want it to do. It equals 7 at negative 8. It equals negative 2 at 10. And so it is good. So final answer, I guess, right there.